Él habla bastante español y entiende español, aunque su plática es en inglés porque es difícil traducir lo que ha aprendido uno en inglés de repente en español, no sabe cómo hacerlo, sobre todo en matemáticas. Es un grato placer tener a Johannes Rau en el instituto. Oficialmente su primera visita al instituto en forma oficial, aunque ya ha estado en México y conoce muy bien a algunos de los investigadores del instituto. Nos va a hablar el día de hoy sobre Enumeration of Curves via Tropical Geometry, que está relacionado con todas las problemáticas e invariantes de Gromov-Witten en física, en geometría diferencial, en geometría algebraica, etc. Gracias.
Okay, thank you very much. But my talk's going to be in English, I'm afraid. Thank you very much for the invitation. Thank you very much for having the opportunity to talk here. So I want to talk about enumeration of curves. So my plan for today is first to give a brief introduction to tropical geometry in general, maybe 15, 20 minutes. And then I will talk about one of the main applications of tropical geometry is enumerative geometry, in particular problems concerning counting curves. And I want to present two examples, namely Gromov-Witten invariance in the plane and Hurwitz numbers. Okay, but let me start with tropical geometry. And so I'm gonna present it as like a type of algebraic geometry, but over the tropical numbers. So remember that one of the great features of classical algebraic geometry is that you can do it over any field you like, and that's why it has so many applications in complex geometry, in real geometry, in number theory. And today I want to present tropical geometry as a kind of algebraic geometry where we use a special algebraic object as a base, and this is these tropical numbers. So let me start with tropical numbers. So that's very easy actually. The tropical numbers as a set, it's just minus infinity together with real numbers. And then I'll tell you what the arithmetic operations of these tropical numbers are. And for this I use the following notation. So this is what is called tropical addition. I will always write it in quotation marks. It's addition, but in quotation marks. And this is defined to be just the maximum of these two numbers. And then there is tropical multiplication, again in quotation marks, and this is just defined to be the ordinary addition of two numbers. And so that's really, this object together with these operations is what is called the tropical semi-field or the tropical numbers. And and that's really the base for tropical geometry. So let me point out, of course, that this is, it's not a field, of course, what I wrote down here. In particular, if you add up, let's say you can even, if you take tropical addition of the same element a couple of times, then you will always end up with x again. So 5 times x is x again. So this is also called idempotent algebra for this reason, because if you add up the same element to itself a couple of times, you do not do anything different. And in particular, this shows that T is not a field. Since you do not have, I mean, the tropical addition is not a group. You don't have inverses for tropical addition. But still, you can do some kind of algebraic geometry over tropical numbers. When you do algebraic geometry, you look at polynomial equations. So we can look at polynomials over these tropical numbers. Let me Let me give you an example. So let's start with something very easy. Let's start with a linear polynomial. So this is a polynomial in the tropical operations. And of course, we can just rewrite it in ordinary terms as it's just taking, I mean, here I have two variables, x and y, and I'm just taking the maximum of 0, x, and y. So in particular, you see I cannot drop 0 here. This, 0 is not the neutral element for tropical addition, so I should really keep this. Now, if you look at this function, then of course you see it's a piecewise linear function where the linear pieces are given by these individual terms. So let me try to draw the graph of this function. Let me maybe use some color. So it'll be constant 0 here, and then here on top of the diagonal, it's going to be here. It's going to be equal to y, for example. This other piece, it's going to be equal to x. So actually, it's maybe easier to draw this function as follows. I just draw it in the plane, and then I just draw the domains of linearity of this function. So this just looks as follows. Here I have x and y, and then my function is just, it has 3 domains of linearity. Here it's constant 0, here it's equal to x, and here it's equal to y. Let me give you a second example just to, or as a second example, I think I wanted, we start as before, we start with 0 plus x plus y, and then we take minus 1x squared plus 1xy plus minus 1y squared. So again, I could rewrite this tropical polynomial just as a maximum over a couple of affine linear functions. And what I get right here, this is x and y. This will look something like this. We're going to have I'm going to have 6 domains of linearity here, 1 for each term. And here the function is going to be 0. Here it's equal to x. Here it's equal to minus 1 plus 2x, which corresponds to, for example, this term. Here we have 1 plus x plus y. And here we have minus 1 plus 2y. And here we have y. Okay. So that's what these tropical polynomials look like. And now in algebraic geometry, of course, you're interested in the 0 set of polynomials. Now in tropic, okay, the tropical 0 is actually minus infinity, because minus infinity is the neutral element for tropical addition. But of course, these functions never attain the value minus infinity. So we don't have a 0 set in the naive sense, but we can. So the 0 set of such a polynomial is defined different. I denote it by v of f, and it's just the corner locus of this function. So it's really just what you see in these pictures already. It's exactly the parts where the domains of linearity meet. So wait, I should take. So this here, this collection of 3 arrays, that's the That's the zero set of this first polynomial up here. And this collection of edges and rays that you see here is the zero set of this second polynomial. There are several reasons why this is the kind of the correct definition of tropical hypersurface, of tropical zero set of a polynomial. We will see one of the reasons in a second, but maybe let's first collect some properties. So these objects here are called tropical hypersurfaces in general, and since I only have two variables, they are called tropical planar curves in this special case. Let me collect some properties of these objects. So first of all, as we see in these examples, let's give this a short name. Let's call it C for curve. So such a tropical curve is just a graph embedded in R2. We can even say more. We can say it's piecewise linearly embedded in R2, a graph. And the second property is that it's actually a special type of graph, namely all the edges here have rational slopes. So that's something that's true in the examples, and it's also true in general. Edges have rational slopes. So a different way of saying is that for each edge you can find a direction vector along this edge, which is an integer vector. So all these edges have integer direction vectors. And then a third property, that's the really important property, it's called the balancing condition. That's the following condition, that if you look at a vertex of such a curve, and you look at all the edges adjacent to this vertex, and then you take exactly these direction vectors that I just described. So let's say this is V1, V2, V3. And of course, we can always choose these direction vectors to be primitive. So kind of the smallest integer vector in this direction. And then the balancing condition says that if I add up all these direction vectors, then I get 0. So kind of if you pull along all the edges adjacent to a vertex, then your vertex doesn't move. And actually, to be precise, in the general framework, you need to add weights here. In general, each edge of my tropical curve comes with an integer weight, and then the balancing condition says that the sum of the primitive vectors stretched with this weight factor sums up to 0. And actually, kind of all these conditions here, they can be summarized in, or also, if you want, they can be explained by what is called the dual subdivision of the curve. So that's a subdivision of the Newton polytope of the corresponding polynomial. So maybe let me just explain what this means here in this example. So here, this curve, it was a conic curve. It's a curve given by a quadratic polynomial, and the Newton polytope is just you take the all the exponent vectors of your polynomial. So this is, these are these 6 exponent vectors which show up in this polynomial. You take the convex hull. That's the Newton polytope of the polynomial, and then you see that you can kind of subdivide this Newton polytope to get something which looks dual to the thing here above. And in this case, the subdivision looks like this. So, I'm not going to explain this in detail, but in general, this duality works as follows. You'll get a subdivision to each of the cells, to each of the triangles of your subdivision. You have a vertex in the curve. To each edge in your subdivision, you have an edge in your tropical curve, which is actually orthogonal to the edge in your subdivision. And then to each vertex of your subdivision, you have one of these domains of linearity in the tropical hypersurface. And if you look carefully at this, then actually you see that kind of all these, the 3 combinatorial conditions that I wrote here, they are encoded in this subdivision, because the rationality just comes from the fact that here you're always connecting integer points, and the balancing condition actually just means that if you pick one of these triangles and you kind of then it just means that if you go around the boundary, then the triangle closes up. So actually, from this you can also see that these weights, they come up as soon as one of the edges in this dual subdivision is not primitive, but has more integer points. Okay. And actually it turns out that these 3 combinatorial conditions on top here, they are sufficient to describe tropical hypersurfaces. So it's also true that any graph which satisfies these properties can be described by a tropical polynomial. So really these tropical curves are really very combinatorial objects. And let me define I want to define 2 things here. I want to define the degree of a curve. So the degree of C is just going to be the degree of the corresponding polynomial. So here we have examples of a tropical line and of a tropical conic. And let me also define the genus of a tropical curve. So for the genus, I would like to say it's just the number of cycles that show up in the graph. So I would like to write just this. But actually, we should take something slightly different. I'm going to give you an example. We're going to take the minimum first Betti number of any graph which can be used to parameterize my curve C. So that's a parameterization. I'm not going to explain in detail what the parameterization is. I'm just going to give you an example. So maybe first let me draw a cubic curve. So a cubic curve can, for example, look like this. So this is a cubic, something given by a polynomial of degree 3. Here we have 1 cycle. The Betti number of this graph is 1. So this is why this curve has genus 1. But for example, you could also have something like this. So here the graph again has Betti number 1, but here you have kind of a double crossing of 2 edges. And you can imagine that you can parameterize this graph by a graph which doesn't really have a vertex here, but it's just 2 edges overlapping in the image. So this is why this curve here has genus 0. Because it can be parameterized by a tree. Okay. And now, okay, so this is kind of the very basic objects of tropical geometry. You can actually do quite some amount of classical algebraic geometry. You can copy it to the tropical world. So for example, you can prove the genus formula, which is known for classical algebraic curves in the plane. You can prove some counterpart in the tropical world. So as you see here, for example, a cubic should have genus 1, a smooth cubic should have genus 1. That's what's happening here. And there's quite some amount of theory which you can just translate to the tropical world. So maybe that's already interesting by its own, because you have this kind of combinatorial theory which looks like it's some kind of algebraic theory. But of course, there's also some really some actual relations between this tropical geometry and classical algebraic geometry. So kind of to give you an idea of how this relation looks like, let me give you a theorem here. So we're going to need the following map. We're going to need the logarithm map, which is, it goes from non-zero, a tuple of two non-zero complex numbers to R2. And it's just coordinate-wise logarithm. So you map CW to the logarithm to base t of the absolute value of z, and the same for the second coordinate. And now, given a polynomial, given a tropical polynomial, I'm going to write it like this. I'm going to write it, so these are the coefficients aij, x to the I, y to the j, everything in quotation marks. Given such a polynomial, I'm going to define a classical, like a usual polynomial. It depends on this parameter t in R. And it uses the coefficients of the tropical polynomial as exponents of this parameter t. So it looks as follows. It's just t to the a ij, and now z to the I v to the j. So you should think of this as a complex, if you want, a complex polynomial in two variables, and it's actually a family of complex polynomials controlled by this parameter t. And now the relation to the tropical world is as follows. So what you can do is, that's a usual polynomial. You can take the honest zero set of this polynomial. You can map it under this logarithm map to R2. It's kind of drawing this curve on logarithmic paper, and then you can take the limit. So let me write all this down. It's going to be the limit when t goes to infinity of the image of the zero set of this polynomial. I mean, I'm only looking at zeros in C star 2. And my claim is that this limit is exactly the tropical curve, the tropical hypersurface associated to this polynomial. So let me give you one example for this. It's actually not so standard example that people use is this line. Let me do this as well. So let's do this procedure for this linear polynomial, the very one on top. So then my polynomial ft is actually just constant. It's t to the 0, so it's 1 plus z plus w. And the zero set of this, okay, I can only draw the real solutions of this polynomial. It looks like here we do not take the zeros where some of the coordinates are 0, so it's just a line. Then the first step is to draw this line in logarithmic coordinates. So if you do this, this is going to look actually something like this. So you can actually see exactly these three segments of the line. They will form these three arcs of this image. And if you also look at the complex solutions of this equation, then you're also going to get the interior of this picture. This is what is called the amoeba. And then we take the limit. So in this case, taking the limit is kind of boring because here, as I said, this polynomial doesn't really depend on t. And then taking the limit just means shrinking everything, scaling everything to the origin. So the only thing that will survive are kind of these asymptotes of this picture. So you will exactly get this line. Okay, but maybe you can imagine that if you do the same thing with this conic, for example, then the amoeba might look something like this. Okay, this is too much in one picture. But it's something, the amoeba is going to be something like a fat version of this curve. And when you take this limit, you kind of starve this amoeba, and all that remains is this skeleton, which is the tropical curve. Yeah, and this process, it's just in a nutshell, this process is called tropicalization, and it gives you a way to relate classical algebraic varieties, families of classical algebraic varieties, to tropical objects, in this case, to tropical curves. Okay, so this is kind of the basic framework of tropical geometry. Now, of course, I promised to give you some applications of this theory. Now, I'd like to start with chromophyton invariance. So I want to explain to you that these tropical curves can be used to compute certain chromophyton invariance. And let me start with kind of the maybe one of the most famous examples for this. So I'm gonna start with some enumerative problem. So I'll define for you the number nd. This is gonna be, maybe I should first tell you what we're going to fix. So we fix some degree, and we fix, so we set n to be the number 3d minus 1, and then we pick n points in the plane. So let's say we pick points in the complex projective plane, but you can think just also of the complex plane C2, fine enough. Just we should choose our points generically. I'm not going to say what this means exactly, but we should kind of take a random collection of points. Then nd is defined to be the number of rational curves, rational algebraic curves, in CP2, passing through all of these points. So maybe but that's one of the, okay, let me just, to make sure that everybody So the kind of the trivial first case is when d is equal to 0, and then the problem asks you choose two arbitrary points in the plane, and then you ask how many, of course I forgot the most important curve of degree d. Of degree d. So here we're looking for algebraic curves of degree d, which means lines, so there's just one line passing through 2 points, and actually the same is true for d is equal to 2. Here you fix 8 points, and then you can show quite easily that there is exactly one ellipse in this case, which passes through 8 points, 5 points, thank you. And then let me draw maybe for D, 3, 4, 5, I already don't remember exactly, maybe. 3, the number is 12 rational cubics passing through 8 points. And here this number is 640, and this is something, I think, something like this. And then the next one is already something like 26 millions, approximately. So these numbers really grow very, very fast. So this is one of these typical kind of enumerative problems that were studied end of 19th century already by Zeuthen, for example, by Harnack, by Schubert. Of course, the important thing here is that if you look at curves, or complex curves, then this number does not depend on the actual position of points that you choose. The curves you get, of course, they depend on which points you start with, but the number does not depend on the. This is really kind of the difference to the Greek geometry, where you actually wanted to construct the curves. Here we're only interested in how many curves do we get that satisfy a certain problem. And so I should say maybe that in the Say it again? Yeah, we'll actually talk about this in a second. So here I really mean all these points are distinct, and I don't have any tangency conditions. I only want to pass through the points. But in a second, I also have a problem where you have kind of multiplicities in the sense that you require a tangency condition at a point. Okay, but so I think these numbers were known in the old days only up to here, this one, and then there was a big in the 70s and in the 80s, 90s when certain ideas in physics and string theory came up, and these problems were studied from a new point of view, and then finally I think there is the famous Kontsevich formula from 94, maybe, which gives a recursive formula to compute all these numbers in once. So this was, at the time, I think it was a quite celebrated result, because really, before there were no ideas whatsoever how to go on. For each step, for each D, you needed a new approach to compute these numbers, and then with new ideas and with the advent of chromosome theory, it became much easier to compute these numbers. So now let me tell you how to compute these numbers tropically. Just check. Or actually, let's first go to your question and let's talk about a second collection of numbers. So this is maybe the first problem. And now let's mention a second problem. So here I'm gonna fix again a degree, and then I'm gonna fix a number n also. Okay, should also be greater than 0. And then I'm gonna fix some yeah, let's say some multiplicities, k1 up to kn. There is some numerical condition that this makes sense, so that the sum of the ki plus 1 should be equal to 3d minus 1. And then you can pose a similar problem to this one. So these numbers I'll call nd, and then they depend on these multiplicities k1 up to kn. Except for, so these numbers, to be precise, I need to use some notation from Gromov-Witten theory, so let me just first write it down. You can define these numbers as an integral over the space of stable maps of P2 of degree D. No, here, I'm only considering the genus 0 case. And we're integrating certain cohomology classes. They look as follows. The pullbacks of classes of points times the psi classes to the power Ka. So this probably is not well known to most of people here, so let me say a few words here. So you should think of this as follows. This here is actually a moduli space of curves, so it parameterizes curves of genus 0 with n marked points mapping to P2 of degree D. And now you have these n marked points, and this first condition kind of asks that each of these marked points should be sent to a certain point that you fix in the plane. And then these here are additional conditions. You can think of it as tangency conditions if you want. It's approximately true. It's not quite true. So what this really is, it's the first Chern class of the cotangent line bundle of the ith marked point. So for those of you who don't know what this means, I'm not going to explain this any further. I'm just going to give an example. I'm going to give an example where this is really about tangency. So let's take d is equal to 0 and k1, k2 is equal to 1 and k3 is equal to 0. So then you fix 3 points, and 2 of these points, maybe this is P1 and this is P2. So here we actually have these higher multiplicities, 1, 1, and here we have 0. And these ones now you can think of it as fixing the tangent lines that our curve should have at these points. So now we're looking for conics which pass through 3 points and have given tangent lines at these 3 points. So again, it's actually quite easy to check that there is exactly one conic which satisfies these conditions. So again, I can only show you kind of boring examples in the sense that this number is always 1. So this would be an example for this. Okay, so now I forgot which blackboards are still available. I think this one is. Now let's go to the tropical version of this. So first I want to kind of present the theorem. This is one of the very first theorems in tropical geometry which made all this subject kind of get started. So this is a famous correspondence theorem by Mikalkin, and it says that this number nd can be computed as follows. It can be computed by kind of translating this enumerative problem, just translating it to the tropical world. So what this means precisely is this is a sum over tropical curves, C in R2, but we need to count these tropical curves with a certain multiplicity. And here, you really do exactly the same thing. So you're just fixing the same number of points now in R2, and you look for tropical curves of degree D and rational, meaning genus 0, so they can all be parameterized by trees and passing through these points. So let me kind of copy these examples here. It's not, I cannot really convince you that this works. I can only, this first case in degree 1, remember that all tropical lines look like this tripod here, but you can translate it, of course. So if you fix 2 points in the plane, then it's quite easy to check that you have exactly one such a line, a tropical line passing through these 2 points. And let me kind of, okay, let me try to convince you that it also works conics. So if you, here I use a trick, I first draw the conic and then I draw 5 points. This is what people usually do. And then also I shouldn't. Now, at least what you can see here is that these 5 points, they kind of, they fix this conic completely. You cannot move you cannot change the length of the edges here or move the conic while still passing through these 5 points. Actually, you can check that there is no other conic. So for example, no conic which looks like the one over there, which is going to pass through these 5 points. Let me, maybe I should say a word about these multiplicities. It's kind of unfortunate that in tropical geometry you do not really count curves, but you actually count curves with a certain weight. Some of the curves you have to count multiple times. It doesn't occur in these examples here. This multiplicity, I can actually, maybe I can write it down to convince you that it's quite easy to compute this multiplicity. It's just, it's the product over all vertices of the curve. And for each vertex, you take twice the area of the triangle in the dual subdivision. So remember, at some point I talked about this dual subdivision. Here, in this case, all the triangles, they have area 1/2. So twice this area is going to be 1. So this multiplicity of this curve is going to be 1. But sometimes you have triangles of bigger area, and then you need to count curves with a certain multiplicity. Okay, now let me mention second theorem about these more complicated invariants. Oh no, I have it here. So this is a result by myself together with Hannah Markwig from 2008. And it says that these numbers, you have these multiplicities k, n, they can also be computed tropically, again as a sum of tropical curves. And it's very similar. So now again, you count, these are rational tropical curves of degree D passing through the marked points. Now, how do these multiplicities come into play? Actually, now we do not want the curve just to pass through a point, but if we have some of these multiplicities non-zero, then we want a vertex at these points. So more precisely, the valence of, okay, let's write it different, at the point pi, the curve has a vertex of valence ki plus 2. So if ki is 0, then, so by valence I mean the number of edges which are adjacent to a vertex. If the valence is 2, then this is actually not a vertex, but just interior point of an edge. But for higher ki, we really need vertices at these points. So here's my example. If you take some points, and let's say these one here have higher multiplicities, 1, 1, and 0. And then, for example, a tropical curve, which you should count, looks like as follows. It should have a vertex here. It passes in the usual way through this vertex here. And then it should also have a vertex here. So this would be a curve that you should count. Okay. And I should maybe make a few remarks here. So I already said that these numbers, in general, they are really hard to compute. So when Grisham-Mikalkin came up with this correspondence theorem, it came kind of as a surprise that you can actually reduce this curve counting to a fairly combinatorial counting on this side here. I mean, you can really turn this into a finite algorithm to compute these numbers. And these numbers, they play a quite important role in, of course, well, they are Chromov-Witten invariants. They are related to subjects coming from string theory, from physics. They are involved in this subject which is called mirror symmetry. They have they are of quite an interest, and they are quite well studied. Of course, I'm only showing here a certain collection. There are more results. For example, you can extend Grisha's Mikalkin's result to other toric surfaces. You can go to higher dimensions, and sometimes you can also go to higher genus. So here I only talked about genus 0. Okay. Maybe questions up to here? Yes?
The closure formula for the classical problem, as Consevich did for the ND problem.
So actually what people did when this result came out, they reproved Konsevich's recursive formula in the tropical world. Mm-hmm. This you can do.
Yeah, but I'm asking about your formula with the case.
Uh-huh.
In that with the case.
In this case,
yes.
You do not get a formula as easy, a recursive formula as easy as the Konsevich one, but you can, both of these problems, you can kind of, on the tropical side, so you can use this freedom of choosing the points. You can choose them, I mean, you should choose them generically, but you can still choose them in a special generic configuration, such that your problem really turns into a purely combinatorial problem. And then you can give formulas for, or at least you can give an algorithm for computing these numbers. So I think I'm running out of time to say much about Hurwitz numbers. Maybe still let me try. So now I should erase. So how do I erase? Oh, I have like 3 minutes left, is this correct? Yeah. So chromoswitten invariance is one big field of a certain type of enumerative problems that you can study. Another one is Hurwitz numbers. It's also about curves, but it's slightly different. So here you look at maps between two curves. Particularly, we're going to look at maps to CP1. So I'm going to draw my pictures two-dimensional. I'm going to think of them as surfaces here. And the idea is as follows. I mean, you fix some points on CP1, and again you fix a degree, and you fix a genus, and then you also fix partitions. Of D. And now you're interested in counting all maps from a second Riemann surface or from an algebraic curve over C, depending on your point of view. So this C, it should, of course, have the genus which is given. This should be a holomorphic map of degree D. And then remember from complex analysis that a holomorphic map, it can have branch points, ramification points of various orders, and these partitions, they prescribe the ramification profile that I want to have on top of these points, P1 up to Pn. So for example, on top of this point P1, I'm going to have a certain number of pre-images, and the ramification indices of these pre-images is exactly encoded by this first partition, alpha 1. And I can count these numbers, and this is what is called Hurwitz number. Of course, I should count modulo isomorphism. These numbers, again, they have been studied intensively, especially in the last years. And I cannot tell you too much about this now, but I'm going to tell you that these numbers also, they can be computed tropically. So there is a result by Cavalieri, Johnson, Markwich, which So this is a result only for so-called double Hurwitz numbers. That means when you only have two ramification points with a special ramification profile, actually you're allowed to have additional so-called simple branch points. So simple branch points are kind of, we don't write the ramification profiles which look like this. These are called simple branch points. We drop them in the notation. And these double Hurwitz numbers, they are already quite interesting and quite complicated. And you can, again, it's kind of very similar. You can count them by counting certain tropical covers. And let me just give you an idea of how such a tropical map looks like. The base in this case is just the real line R. And then we fix some points on this base. These points will correspond to simple branch points. And then on top of these points, we we're supposed to have a graph again. So this here is gamma. It's a graph. It comes with a map with a projection to R. And again, the edges of this graph gamma, they have weights. For example, this here could have weight 5, and then 3, 2, 1, 1, 4. Again, you see there is some kind of balancing condition. The balancing condition here is that I'm not going to write it down. The balancing condition is just that the sum of the weights of the outgoing edges is the same as the sum of the weights of the incoming edges. And if you count these pictures with a certain multiplicity, you get these Hurwitz numbers. And let me just finish so I just want to also mention more.
Those graphs are not tropical.
You can think of them as abstract tropical curves. So they are equipped with a metric, actually. I mean, the metric is induced by the distances between these points here. And so what I did this year is a result about the real version of this problem. So I haven't told you anything about real enumerative geometry so far, but let me kind of do it by brute force. So you can do the same, you can pose the same problem in real algebraic geometry, meaning that your map should be a map between real algebraic curves. Then you get what is called real Hurwitz numbers. But the problem with real Hurwitz numbers is that they actually do depend on the arrangement of branch points that you choose. So here, let me call this collection of points, let me call this script P. So this is number of real curves, and then etc. And for these numbers, so far there was not much known. So in particular, it wasn't known if such real curves exist, if these numbers are non-zero, or in which cases they are non-zero. And using this tropical description that I just mentioned, I defined a number which I call as zigzag number. It counts, actually in here we don't need multiplicities, it counts a certain subcollection of these tropical covers, which are called tropical zigzag covers. They are of very special combinatorial type, which can be described explicitly. And the main properties of this zigzag number is that it's a lower bound for the number of real solutions of your enumerative problem. So of course, the number of complex solutions is an upper bound. Let me use the superscript C here. So these numbers give a lower bound for the number of solutions. You can give criteria when these numbers are non-zero. And most importantly, you can show that on a logarithmic scale, if non-zero, then these numbers grow as fast as the complex numbers. So the logarithm of these zigzag numbers is equivalent, when you increase the degree, to the logarithm of the complex numbers, which tells you that like on a logarithmic scale, you have as many real solutions. I mean, of course, it's a very rough estimate, but it's what you typically get in real enumerative geometry, that on a logarithmic scale, you have as many real solutions as complex solutions. Sorry for going over time. I'm going to stop here.
¿Preguntas? ¿Comentarios?